Just want to say before we get started, like we said there, we know it's the end of a long couple of days and there's been a lot of talk, so we both really appreciate you all coming to listen to our presentation and hope you enjoy it. We'll try and keep it light and breezy, but hopefully you get something from it. I'll pass over to Anna to start off with.
Thank you so much for coming, guys. It's really great to see so many of you. I realize we are the only people stopping you from enjoying yourselves and the beer afterwards, so as Adam said, we'll keep it brief. So we both work for a company called Elsevier, which is a global information analytics business that specializes in healthcare and science. We started as a small publishing house in Holland at the end of the 19th century. Now our products are used by over 25,000 academic and government institutions around the world. We still publish debt-free formats like journals such as The Lancet, but we also have a plethora of digital products. Some of them include ScienceDirect, which is a large information portal, Mendeley, which is a free-to-use reference manager and a social network for academics, and Scopus, which is the world's largest abstract and citation database for peer-reviewed literature. Our users are in the world of health and science, and every day they make decisions which impact individuals, nations, and governments. To them, knowledge is paramount, and it's our job to make sure that they have access to information that is both reliable and current. Adam and I work in recommender systems at Elsevier, building recommendation engines to help researchers and academics find the most relevant content more quickly. The life of a researcher in modern day is quite difficult. They not only have to teach, go to conferences, apply for grants, they also have to keep on top of their field and the research. That's what they do. The last thing we want them to do is to spend valuable time and brain power on searching through relevant documentation that they need to read. There is something like 420,000 new academic research being published every year. And what we're trying to do is build recommendation engines that surface the most relevant stuff to them. In this talk, we're going to tell you how we build one such recommendation engine for ScienceDirect. As I mentioned, it's a portal with 15 million articles of research that is viewed by millions of unique users every month. This little box over here is what the recommendation engine looks like. As usual, with backend work, it doesn't even begin to convey how much code, sweat, and research went into displaying that little box. So in this talk, I'm hoping to show to you exactly how we did it from scratch. So this is a recipe for a recommendation engine. You take all of your web browsing logs or whatever input data you have, you take all of the items that you're trying to recommend, and you surface top most relevant recommendations. How do we do this? In a nutshell, the first step that we use is collaborative filtering, which generated recommendations for our users. Then we take those recommendations and we rescore them through a learning to rank model. And at the end, we evaluate our model using both offline evaluation before we actually serve those recommendations in productions, and online evaluations using A/B testing. I'll talk to you about collaborative filtering, and then Adam will take over and talk about learning to rank and model evaluation. So we're all at the Spark AI Summit. Everyone knows what collaborative filtering is. Everyone must have heard about the Netflix prize. And the fact that collaborative filtering was the core component of the winning combination of algorithms. It's very widely used in the industry. The beauty of collaborative filtering is that it's a little bit like a brute force approach that doesn't really require too much engineering knowledge effort up front. You basically don't need to know much about the users or the items you're trying to recommend. And you analyze the behavior of your users to build up recommendations through effectively surfacing the wisdom of the crowds. This is basically how it works. In our case, we built a matrix, a usage matrix, which looked at the browsing history logs for every one of our users. The browsing history is tweaked in a time frame that depends, it's very much configurable. So you can look at a whole year's history of browsing data or maybe just a week. It very much depends on how much of the system you want to analyze. At this point, collaborative filtering diverges a little depending on which flavor you want to use. So for example, in personal recommendations, if you go on Amazon's website, it can recommend you items based on your previous purchase history. That's called user-based collaborative filtering. That's when you're looking at similarities to other users and recommending items to the user that you're trying to recommend items to. This didn't really work for us because our users browse ScienceDirect mostly anonymously. So we had to use item-based collaborative filtering. Taking the matrix from the previous slide, we create a vector representation of each item usage. This is doing a pairwise comparison of all of the vectors, and through applying a cosine similarity formula, it's producing the similarity matrix seen here. What we serve as recommendations is the top nearest neighbors for each given article. So for illustration purposes, the darker the blue, the more similar the items are. You can see the diagonal is the darkest shade possible. In reality, this isn't a color, obviously. It's a score between 0 and 1. This matrix is symmetrical, so it doesn't have to be 15 million articles. By 15 million articles, we can completely get rid of half of the problem. It reduces the computational complexity, but in a nutshell, it's still very much a big data problem, and it requires Spark to solve it. So this is what our recommendation engine looks like at this stage of the process. It runs as an AWS data pipeline, and it's a series of Spark jobs. The first Spark job takes in all of your input data, which is our daily web browsing logs. Now, this is ranging in 1 million of entries per day. We first have to tidy that data and remove any kind of web bots or traffic generated through our own recommendations, because effectively we don't want to have biased views in our system. The next step is another Spark job that takes this as input and generate item-based collaborative filtering recommendations. This data set of recommendations per article is a key value pair of article to recommendations, and we save that, we load that into Redis to be served through an API. Collaborative filtering is great, and it's definitely a fantastic first step. However, we can do a lot better with the data we have. In the next section, Adam will talk to you about what we improved on.
Thanks, Anna. So, as Anna was talking about, collaborative filtering is quite an elegant solution to this idea of recommender systems. It's a good approach. And one of the strengths of it is that we don't really need to know any details about the recommendations we're serving. We don't need to know much about the articles themselves, because it's all based on usage. But there is a trade-off associated with that. Because it's based on usage, it can have a tendency to maybe just recommend things that are popular in general, rather than being specifically relevant to the article in question. It also doesn't take into account factors such as how recently an article was published, and we know that's quite important to some of our users who want to see the most recent things. Recommendations can often also come from the same journal as the source article, and we want to offer something a bit more diverse than that. The question is, can we actually use any of those features we have on the articles themselves to improve the quality of the recommendations? So let's think about what kind of features we have, because at Elsevier we're publishing these articles. In theory, we should know quite a lot about them. Starting off with the collaborative filtering score that Anna just talked about, we know that's a pretty good way of predicting the relevance of a recommendation, so it makes sense to hold on to that as an important feature. We can look at popularity of articles as given by the number of people who have downloaded or viewed an article on ScienceDirect, or indeed how many other papers have actually cited that article in their research. We can look at temporal features, So as I mentioned, the publication year of an article might be very important, as is the relative gap in publication year between a source article and the recommendation. We know that our users want to see the most recent, fresh content, so it makes sense to keep an eye on that. We also have access to a taxonomy that tells us which subject area every article that we publish belongs to. So given a source article and a recommendation, we can quickly see, do they belong to the same wider field of science, or actually do they belong to the same specific subfield, or are they completely different? A particularly interesting feature that we have is obviously the text associated with the articles. We haven't really talked about that yet. So obviously, every research article has an abstract, has a title, probably has a few keywords. And we can, actually what we do, we take that text and we can convert it to a TF-IDF vector, and we use Spark's machine learning libraries to do that. So that gives us a nice numerical representation of the text content of each article. And through that, we can then compare the source article and the recommendation to give us an idea of how similar they are in terms of the text content. So intuitively, that's quite an important feature and something we could make use of. The question is, using all these features and more besides I haven't talked about, what can we do with them to improve the quality of our recommendations? So that's where the whole learning to rank approach comes in. It's also referred to as machine-learned ranking. Learning to rank was originally employed by information retrieval engines, such as search engines, in order to rank results in the best order possible. The approach has also been used in recommendation systems, such as those at Netflix and YouTube. And in the image here, you'll see an example from YouTube that I made up. Here, a learning to rank model is employed to take some recommendations and display them in an order where the most relevant recommendation is presented first. I should just point out, these aren't my personal recommendations, but it's just something I pulled off the web. The model works by looking at features that describe both the query and the recommendation itself. In our case, for ScienceDirect, we have a query research article, we have a recommendation article. We can look at features associated with both of those and then come up with some prediction for how relevant the recommendation is. Rather than being trained on manually labeled data, the model itself is trained by what our users are clicking on in terms of the recommendations. And in that sense, it's the users themselves actually teaching us what's the best way to rank these recommendations. So what does an LTR model or learning to rank model look like? Well, it's described in the literature as a gradient boosted tree, but in very simple terms, it looks something a bit like this. Here we use numerical features that describe a house, and using those, we end up with a predicted value for the price. So you traverse the tree, you look at a particular feature, for instance, the area of the house in square meters, what age the house is, how many bedrooms are in there. And by traversing the tree, you end up with a prediction. And that's essentially what we want to recreate with our recommendations. We want to end up with a predicted relevance, given a set of numerical features and weights associated with them. The question is, how do we actually build a model like that? So to build a model, there's 3 steps, really. We need some input training data, first of all, and that's going to represent the user behavior we're trying to predict. So in this case, just an example, imagine there's this article on Apache Spark on ScienceDirect, and a particular user has clicked on 2 of those recommendations. Now, if we take that data and we take the same data for all of our users and all of our articles and aggregate that through Apache Spark, we can essentially end up with what looks like an idealized recommendation data set, where we have source articles and recommendations ordered by a score, which is representative of the click-through rate. The next step, once we have those recommendations, we need to enrich them with some features, like the ones I described previously. So we take the article feature data set, we have some collaborative filtering scores, as Anna talked about earlier. We join those to that recommendations data set, do a bit of formatting, and eventually we have a data set that we can use to train a model. So this enriched data is then split into 2 parts. 80% of that data is used to train a model, and the remainder is used to validate the model. That is doing things like hyperparameter tuning and feature selection. The split is obviously quite configurable. That's just a value we found to work well. obviously you've got a compromise between the model performance and overfitting the training data. Once you've done that, an iterative algorithm is employed to generate and evaluate new trees until we eventually converge upon a single model. At this point, we now have something we can use to predict the relevance of the recommendations that we're generating. So now we have a model, we need to apply that to our recommendations, the ones that are produced by our collaborative filtering pipeline. And eventually we'll end up with a set of rescored recommendations. So again, we enrich those recommendations with the article features, much like we used to train the model initially. We then take those models, and in Apache Spark, we apply the LTR model. And eventually we end up with these rescored recommendations. The resulting data set contains all the same recommendations that we had originally, but they now should be rescored and hopefully reordered in such a way that the most relevant recommendations are at the top. So how do we know this actually works? Obviously, we can do some offline analysis. We can take some user behavior from the past, see how well these rescored recommendations predict that behavior. And that's certainly good, but it's only really a best guess at how good the model is. So to know how well it's going to work, we need to take it to an online context and try it out in real people. And some of you probably would have heard about A/B testing before, if not everyone. So this is a technique really for experimenting with components on a web page. So in some cases, it may be just trying to test out the new design of a button or something simple on a web page like that. But in our case, we're going to use it to experiment with the alternative recommendations for a particular article. So how does it work? Basically, when users arrive on the web page, they're added to a bucket, either a control bucket or an experiment bucket, or the variant in this case. The users in bucket A just get the usual collaborative filtering recommendations like they would normally. Users in bucket B get the rescored recommendations, and there should be an equal volume of traffic to each one. While this is happening, we're collecting a number of key metrics that represent how much our users are engaging with the recommendations. That way we can compare which is better. So I've described a system here, and this is something we've actually done in production now. We've run this test. So the question is, how well did it work? Did it actually improve recommendations? And we measured user engagement across 6 key metrics, and each of them showed a statistically significant improvement of between 7 to 10% for the rescored recommendations using the LTR model. And that was a big win for us. It's a big deal, and it's quite a clear step forward over the vanilla collaborative filtering recommendations, and that made us very happy. And that's something we've now put into production today, so when you go to ScienceDirect, you should see recommendations that have gone through this model. And just to illustrate how happy we were, I prepared a little GIF. I would like to point out that our team is a bit more diverse than the Microsoft executives there, but we were very happy with that result. Okay, so now we've proven that the learning to rank model works. We've done an A/B test to show that. So how can we actually take that further? So when I described how we trained the model originally, that was on some user behavior for a certain time frame. So it stands to reason as time goes on, we can train more models because we've got more feedback. We can then try those new models out, we can evaluate them in an offline context, and then compare them to the current model we have in production. If that model shows an improvement, we can then promote it, and that'll be our new production model, our new champion. Of course, while all that is going on, we're collecting more and more feedback data, and so the cycle continues. We can keep training, evaluating, and promoting new models. And this can all be automated. So really the key thing is here that once this cycle is in place, we can have recommendations that should improve by themselves over time without any manual intervention. So just to update the earlier slide on what our pipeline looks like, this is what we're hoping to get to now. So we have the primary pipeline, as usual, doing the collaborative filtering to generate some recommendations. At the same time, we have a parallel pipeline that's collecting the user feedback, how they're clicking on the recommendations, creating those training data sets, training new models, doing the evaluation. We're then promoting that LTR model into our primary pipeline to rescore our recommendations. And like I say, this should be happening periodically in batch, and the model should be improving over time as feedback's coming in. And obviously that's really the goal of all this work, really, is to end up with a system that improves itself. And hopefully we don't have to do much work. Thing to note here, obviously, is all this is happening, pretty much every step is an Apache Spark job. We use Amazon Elastic MapReduce and data pipelines to orchestrate that, but clearly Spark is key to all this working. Okay, so now the final stretch. Let's just summarize what we've covered so far. To zoom out a little bit, let's just think about why we did all this in the first place. So we know researchers are trying to find that metaphorical needle in a haystack. There's a mountain of literature out there they've got to sift through, and it's only growing all the time. If we can deliver some quality recommendations, we can really make a difference to their efficiency and help them make breakthroughs more quickly. And ultimately, it's going to be a benefit to everyone here and humanity as a whole, if you want to be grand about it. So that's why we do it. In this presentation, we've seen how collaborative filtering works pretty well. It's a good start. And it's a very elegant solution to a difficult problem. But we know we can do a bit better. And that's where learning to rank comes in. We have a wealth of features that we can use to improve the relevancy of our recommendations. And we can make even better predictions about what our users find relevant. And we were able to prove that through an A/B test and trying out in real users. And now, as we move forward, we're going to start building towards this adaptive model, where our LTR model is going to improve by itself over time. So the quality of our recommendations can only get better. And that's a great thing. So I would be remiss, of course, before I get to that. So obviously Apache Spark is the foundation for everything here. Whether it's processing the user click data, performing collaborative filtering, whether it's deriving those article features like the TF-IDF vectors, whether it's rescoring our recommendations with the learning to rank model, that's all powered by Apache Spark. And importantly, it's a framework and a common reference point between our engineers and our data scientists. Everyone on the team knows how to use it. It supports all of our workflows, from the standard ETL things that we do to the complex machine learning that our data scientists experiment with in notebooks. And when it comes time to put that complex machine learning into production, much like learning to rank was once upon a time, our engineers and scientists are able to work together to make that happen. Spark enables all of those things, and that's why we love it. So, of course, shameless plug again. As everyone is, we're hiring. We're always on the lookout for very talented engineers and scientists. So if anything we've covered today has piqued your interest, then please come and speak to either Anna or myself. And there's a link to the Tech Careers page. And again, thank you very much for spending your last talk with us at the summit. I hope you've enjoyed this and the summit as a whole. And thank you. And if you have any questions.
Thank you. We have a little bit of time left for questions. So, anybody?
There's one behind you.
Ooh.
Hi, thank you for the great presentation. I was curious about the key metrics you are using to validate your model.
Oh, you mean in the A/B test?
Yeah.
So in the A/B test, we're looking literally at people downloading or viewing the full text of a recommendation for a given article. And in terms of the offline stuff, we can look at metrics such as precision and recall. There's a range of metrics that show how well the recommendation is predicted and actual users' behavior. Did we get the right articles in the right order, that kind of thing. But yeah, for A/B tests, it's literally just have they clicked it and variations of that.
Okay.
Hey, thank you for the talk. Quick question. As far as I understood, you're taking this collaborative item-based filtering, and then you're like, the user has given 5 items, and he's maybe choosing one, and then you're using this data to retrain or to optimize your model. But for me, this somehow sounds like you're overfitting, because you're already, the user is already biased by the 3 or 4 recommendation he's seeing, and then you are just using his interaction again to retrain your model. Did you deal with that, or have you thought about it?
So I think I mentioned it, but when in the ETL, when we process our weblogs, we actually explicitly remove all of the recommendations that were clicked because we served them to the user.
Yeah, so we don't want to get into that feedback loop where people accessing recommended articles are then powering further recommendations. But when it comes to training the LTR model, yes, we do use what they're clicking on in terms of recommendations as a way to train that. Yeah, I'm trying to think of a good way to explain that. But
Which part do you think is problematic with overfitting? Is it the original collaborative filtering or the learning to rank bit?
Sorry. Yeah, as far as I understood, you're using this collaborative filtering, and then, I mean, you think that's not the best possible recommendation, right? That's why you later bring in the user's behavior to retrain another path to bring it in. So, but the user, I mean, if there are like 10 good books matching to one specific, you're just like offering him 3 recommendations based on the first stage of this collaborative filtering, and then he doesn't see the other 7 in case of you show them 3 and there are 10. So he's already somehow biased by your first recommendation. That's my understanding. Yeah, and if the first model isn't really good enough, you maybe miss a really, really good other recommendation which isn't shown to him.
I mean, how do you define a good recommendation, right? In a neighbor similar based approach, it is the one that is the most similar out of all the other articles. So we choose the top most similar articles, and that's what we show to the user. That's, let's say, 20 or 30 articles. We then rescore those articles using the learning to rank model. We can take this offline if we haven't explained it clearly enough. Sorry.
I think the key here is the learn to rank model only applies to a context where you have a query, which is the source article, and some results, which is our recommendations, which comes from the candidate set from collaborative filtering. And then the learn to rank kind of modifies that limited set of results. So that's why we use the clicks on the recommendations, but we can talk more about that.
Last question.
I have a related question, actually. If the recommendation is really, really good, it may be that the person already downloaded the paper you're recommending last week or last year, so will not download it again because he knows it already. And that will be, you will considering that as a bad recommendation because it has not engaged with that, but in fact it was so good that he had seen it already.
Yeah, I think you're quite right. That would be an issue, and if a sizable population of users had indeed already made that link between those papers, then yeah, that makes sense. And certainly, we talked about a non-personalized recommender here, but we also have personalized recommenders, right? So we email ScienceDirect users with recommendations, and in that context, we definitely don't send them stuff we know they already accessed. But for this kind of non-personal, anonymous recommender system, we don't really have the ability to do that because we don't know anything about the person who's looking at the recommendation. But yeah, that's definitely a hazard that you can run into. Certainly, we've run into issues where we recommend articles that the person has authored. And I mean, in a way, it's good because it means we're on the right track, but it's also a little embarrassing.
But there is really no way of knowing what else to do if the majority of our users don't log in. We don't track them by cookies and try to tie it into any kind of specific user.